let's look at our real-world application problem. So this graph shows the height, y, in feet of a soccer ball x seconds after it's kicked from the base of a hill with an initial velocity of 20 feet per second. And the linear function represents the hill that has a constant slope. So this is the path of our soccer ball right here, starting at the base of the hill, and it's going to come up and it's going to land on the hill right here where that parabola intersects the line. Now we can kind of estimate what that intersection is, probably at about 1.2-ish, but I want to be more accurate than that. So we're going to need to actually write some equations for these graphs and go ahead and find the intersection. Now we could write the equations by hand using the points that we have, but we'll use the power of Desmos to do the heavy lifting for us. I want to determine some points for the parabola and the line. Remember that we need 3 points for a parabola, 2 points for a line. So let's look at the parabola first. I can see that I have a point at 0, 0 and one at 1, 4. I can also pick up a third point right here at this other intercept at 1.25, halfway between 1 and 1.5. So let's go ahead and say 0, 0 is a point, 1, 4 is a point, and the other point is at 1.25, 0. For my line, I also have 0, 0 as a point, and then over here on the other side of the graph, I have 2, 2. So we can go ahead and indicate those 2 points. I'm going to use these points in Desmos to put into a table and then run regressions in order to get my equations. So let's go over to Desmos. Here we are in Desmos, and I selected the plus button and selected to insert a table, and I want to put in the points for my parabola. So I had an x value of 0 and an x value of 1 and 1.25. The corresponding y values were 0, 4, and 0. I have also, in the second line, indicated the equation that Desmos needs to have in order to find the equation for the parabola. So it's basically standard form of a parabola. Y is equal to ax squared plus bx plus c. But remember that we have to use x1 and y1 because of the table indicators, and we also use the approximation symbol to let Desmos know that we want it to create our equation. So we can see that our a value is -16 and our b value is 20. On this same page, I've done an insert another table, and notice that this is x2 and y2 values this time for my line at 0, 0 and 2, 2. I need to indicate y2 and x2 values in my equation for the line, y equals mx plus b, but again with the 2's to indicate the x2 and y2 and the approximation symbol to get Desmos to calculate the numbers. So we have an m value of 1 and a b value of 0. Let's go ahead and go write our equations, and then we'll start taking a look at the intersection. From Desmos, we were able to obtain the equation for our parabola. It was a -16 for our a value, so that'll be multiplied by x squared, and it was a 20 for our b value. And c was 0, so we don't even have to report it. For our line, our mx plus b, our m was 1, so we're just going to have an x, and then b was 0, so it's basically x plus 0 or just x. So now what we want to do is go back and look at Desmos and see where those two graphs intersect. Here we are back in Desmos. I'm going to zoom in a little bit here so that we can see this really well. And I can see that my intersections, there's actually 2 of them at 0, 0, which makes sense because we were at the bottom of the hill at time 0. And then the second intersection is at 1.187 and 1.188, which we could just call 1.19 for both of those. So let's go ahead and go report our answer. Our time, remember, was our x-axis, so technically it's this 1.187, the x value that is going to be our solution. We found our intersection in Desmos. It was at about 1.19 for an x value and also 1.19 for a y value, and that is our intersection point. And so that means that our soccer ball lands on the hill at the x value, because time is x, of 1.19. So it lands on the hill after 1.19 seconds. So that is the answer to part number 1. Part number 2 asks us to just look at the reasonableness of the solution. And so that means, does it seem reasonable given the data that we have? So if we look at our graph, and we kind of already talked about this at the beginning, we can see that our intersection is right here from the graph that we saw before. It's a little less than 1.25. I guesstimated it to be about 1.2 when we first started this problem, and so 1.19 is definitely a reasonable seeming solution. So we can say that looking at the graph, the value seems reasonable. All right, that is it for today, guys.